Hi, I'm Ralph Gable, and today we're going to cover understanding voltage. Now, picture, if you will, a tank filled with water, and at the bottom of the tank you have a spigot, a pipe coming out from the bottom of the tank, and the end of that pipe you have a valve so the tank doesn't just empty. And the most common explanation for voltage is that voltage is like the pressure in that pipe coming out of the bottom of the tank. Well, this is actually a very simplified version of what voltage really is, and it suffices for most people, and that's just fine. But it doesn't actually describe what voltage really is. And being that you are the inquisitive experimenter, you want more than just that. You want the real story. And that is my goal in this video. Now, voltage is not an easy thing to understand. I've spent a lot of time just working through it in order to try to be able to explain it well. And so, in order to make it into something that we can feel in our bones, we have to review some basic physics. First of all, we're going to answer the question, what is the makeup of the atom? Second of all, we're going to be talking about gravity, which of itself is a very difficult item to completely grasp. Thirdly, we're going to be talking about work. Fourthly, we're going to talk about potential energy. And lastly, we'll talk about what is a coulomb. Now, once we cover all those things, then we'll start relating it all to what voltage really is. So with that, let's move on. To begin with, we have to remember that atoms are made up of three basic particles. One is a proton, which is a positive particle. There are neutrons, which are neutrally charged. They're just there. And then there are the electrons. Now, the protons and neutrons make up what we know as the nucleus, and they just kind of get all bunched into the center, and you can have one or more protons that are part of the nucleus, and then most atoms have more than one neutron. Circulating around this nucleus are the electrons out here. These are spinning around a lot like our planets spin around the sun. So you can kind of think about the nucleus as being like the sun and the electrons being like the planets. Now, as you can probably guess by looking at this, the electrons are the mobile part of this whole atom. And so it is possible for an electron over here to come careening into this atom, hit one of these electrons. One of these electrons then goes careening off in a direction, and this guy takes its place in the atom. So the atom remains neutral, but this electron hits this electron, that electron continues on, and guess what? It gets to hit yet another atom's electron and displace it. Now, some atoms are more likely to allow this kind of thing happen than others. And it just depends on the particular material that we're talking about. But the main thing to remember, to take out of this, is that the electrons are really the mobile part of this whole equation that we're talking about here. And so now we get to talk about gravity. Well, you know, gravity, no one seems to really know what gravity is. There's about 5 different theories as to what gravity is, and Einstein theorized, and various people did, and it's associated with, I mean, everything that has mass has gravity, but going into exactly what gravity is and why it is beyond anything we're going to try to do here. People a lot smarter than me still can't agree on what it is. Suffice it to say, gravity just is. Now, we can only explain it in terms of the effects that it has on our universe. And one of these effects is what's called the gravitational constant, which means that stuff falls and things accelerate as they fall. So knowing how long something has taken to go from the rim of a canyon down to the bottom of a canyon, you can sit there knowing the gravitational constant and calculate how deep the canyon is and how fast the rock was going before it hit the bottom. The gravitational constant is 32.17 feet per second squared, or 9.8 meters per second squared. Those are the standard values for the gravitational constant. Now, weight is the force that an object exerts on the earth due to the effects of gravity. So weight is a force. That's what you feel on the bottom of your feet as you're standing there. Force is equal to mass times acceleration. Force equals mass times acceleration. That is a standard physics principle. So the weight of an object, because weight is force, the weight of an object is force, therefore the weight of an object is the mass of that object times the gravitational acceleration. So if we were to do a quick problem here, let me reset the board. If we were to do a quick problem here, let's say we had a block of steel. Here's our block of steel. Now let's work in the English or system, otherwise known as the imperial system. And so in the imperial system, mass is in slugs. Yeah, slugs. They're not slimy things, they're slugs. So we have a block of steel that has a mass equal to 1 slug. Now, we know the gravitational acceleration constant is equal to 32.17 feet per second squared. And we know that force is equal to mass times acceleration. So therefore, the weight of this 1 slug block of steel is going to be 1 slug times 32.17 feet per second squared. In other words, it will weigh 32.17 pounds. So you have gravity, which is unexplainable, but it is. It is experienced in our world, in our way of doing things, in the gravitational acceleration, which produces weight due to that acceleration. And as a matter of trivia, this is also equal to 2.298 stones. You got to love the English system, don't you? Now, there's one thing that we have to remember here that's going to be important for us. And that has to do with the unit of force in the metric system. Now, we all hear about going out and buying a kilogram of meat, or, you know, that somehow kilogram is a measure of weight, but it really isn't. In the real metric system, the official metric system, the unit of force is the Newton. Kilogram is mass, Newton is force. When you go out and buy a metric torque wrench, it is rated in Newton meters, not in kilogram meters. So that's an important thing to remember, that Newton is the unit for force in the metric system. And so now on to our next topic. And so now we're starting our next section on work. Work talks about the measurement of energy expended to do something, to move something from one place to another. And as such, it is defined as work is equal to the force times the distance. The units in the metric system are joules, and the units in the English systems is foot-pounds. So, if I have a box that weighs 10 pounds, it takes 10 pounds to lift it. That's the force necessary to lift that box off the floor. And I lifted it up to a shelf that was 5 foot off the floor. Then that means I would be doing 10 pounds lifting force times 5 feet is the distance I'm moving it through. I would be doing 50 foot-pounds of work to move that. That is an expression of the amount of energy necessary to move that box up onto that shelf. So now we're going to go over into the metric system, because in electronics everything is done in the metric system. We talk about joules of energy in electronics. And so we're going to have a 10 Newton box. That means it weighs 10 newtons. It takes 10 newtons of force to lift it off of the floor. And we're going to lift that box onto a shelf that is 3 meters off of the floor. So we have 10 newtons of force being applied to a box to move it 3 meters, which gives us 30 Newton meters of work, which is the same as 30 joules of work to move that box from the floor up onto the shelf. So work is an expression of the energy expended to do something. That's an important thing to take away from this. It is a measurement of energy expended to do something, and is equal to the force times the distance. Now on to our next section. Okay, our next topic is potential energy. Now, potential energy is very similar to work. It is a complement to work. We already learned that work is the energy expended doing something, and the units used for work are joules. Potential energy is energy that is available to do work. So, if we had a 10-pound box down here on the floor, relative to the floor, this 10-pound box has 0 potential energy relative to the floor. It can't do anything, it can't do any work, because remember, work is force times distance, and it's already touching the floor. There's 0 distance, therefore there is 0 ability to do work. If, on the other hand, we were to take this 10-pound box and lift it up onto our shelf that was 5 foot off of the floor, we already showed that we would be doing 50 foot-pounds of work to move our box from the floor to the shelf. So that is the energy expended. Now, relative to the floor, we have just increased the potential energy of that box 50 foot-pounds because we have it now on this shelf that has somewhere to go. Relative to the shelf, it has 0 potential energy. So potential energy is energy that is available to do work. So now this box possesses, sitting on this shelf, energy available to do work on something on the floor. So if perchance the shelf were to just somehow magically disappear out from underneath the box could then fall because of the potential energy that's in it and the forces associated with gravity, and do 50 foot-pounds of work on whatever it happens to fall on the floor. So the takeaway on this, potential energy is the energy available to do work and is a complement to work, which is energy expended. On to the next section. Okay, now let's just trace all of this back through. We discovered that gravity, well, gravity just is. And it is experienced as a result of the effects that it has on the universe around it. And one of these effects is expressed in the gravitational acceleration constant. This constant is used to calculate the weight of an object, which is the force that that object exerts on the surface that it's sitting on. We discovered that work is force times distance. It's talking about the energy expended to move an object. And so if we take our box and move it from this level to this level, we've expended energy to do that. We have expended work because we've had to lift against the effects of gravity, and we've moved it through a distance onto that shelf. At the same time, that object, that box up on the shelf, is now increased in potential energy. Potential energy is energy that is available to do work. So work is energy expended. Potential energy is energy that's available to do work. Now, the last thing that we have to cover before we go into our explanation of voltage is the concept of a coulomb. Now, a coulomb, if we were to take our itsy bitsy teeny weeny itsy tiny tweezers and take a sack and pick off electrons and place them in our sack with our itsy bitsy teeny weeny tweezers, and being careful to count every electron as we went and never lose count, if we could manage to put 6.24150975 million trillion electrons in our sack, then we would have a coulomb of electrons in our sack to use. So coulomb is a measurement of charge, and 1 coulomb is equivalent to this very large number, 6.24 million trillion electrons in our sack. So finally, we're able to start talking about voltage. Well, suppose we had 2 objects, and we separated those 2 objects out from each other and got out our itsy bitsy teeny weeny tweezers and started picking electrons off of one object and placing them on the other. One by one, we kept transferring electrons between the one object and the other object. Well, we would end up with a charge difference between the 2 objects. Now, with this charge difference, an electric field would then appear between the 2 objects. Well, you know, like gravity, they cannot really explain why gravity is, Well, they really can't explain why this electric field is there either. It just is. It's a fact of the way it is. You have a charge difference between two objects, and you're going to end up with an electric field between the two of them. And like gravity, there is this attraction business going on. With gravity, you have any two objects with mass that will tend to attract one another. And with these electric charges, we know that like charges will repel away from each other and unlike charges attract to each other. So we can kind of think of the electric field kind of like the electrical equivalent to gravity. So in the gravity world, in the physical world that we can better relate to, it takes work to lift this box from the floor up to a shelf. Why? Because there is a force associated with having to lift the box. There's a distance that we're going through to get it up onto that shelf. Well, this electric field exerts a force on any charged particle that gets into the electric field. And so if we're taking an electron, now remember, the electron wants to be with the positive side. If we have an electron that we have right here next to the positive side, and we are moving it toward the negative guy, well, the positive guy wants to hang on to its electron, so there is that attraction between that electron and the positively charged entity, and there is a repulsion of that electron with the negatively charged. So you're working against this electric field, this force of attraction and repulsion within the electric field because of this charged particle. So if you think about it, you have a distance between these two objects, and you have to exert a force to move it between the two objects. Therefore, you're doing work to move that particle. So here, moving the box from down here, we're exerting force to move it onto the shelf. We're exerting work. We're also increasing the potential energy of the box on the shelf. In this case, as we take this electron from this positively charged guy and move it across here, we're exerting force, we're going through a distance, and we're increasing the potential energy of that electron. Now, suppose that we were to somehow be able to get a very special bag here, and in that very special bag, we are able to use our itsy bitsy tweezers and start collecting electrons over here. Now let's suppose we are able to collect an entire coulomb of electrons. Now, taking that bag of electrons and setting it right here next to this positive charge and moving it toward the negative charge, again, we have charged particles in our bag, and we're moving it through an electric field from one to the other. The electric field is exerting a force on that bag, saying you're not going to move. There's all the attraction and repulsion going on. So because we have to exert force on that bag of electrons and we're moving through a distance, we're doing work to move that bag of electrons in the electric field. If we do 1 joule of work to move that bag of 1 coulomb of electrons from one charged object to another, then we say that the potential difference between these two charged objects is 1 volt. So voltage is an expression of the potential to do work in the same sense that potential energy here is an expression of the potential to do work, having done the work in the first place of moving the box from the floor to the shelf. In this case, we're moving our coulomb of electrons from the positive to the negative. We've done a joule of work here. We do a joule of work here. The potential energy available is 1 joule in both cases. So you notice that voltage is not a force, but is any more than the potential energy here and the work associated with the energy of this box is a force. It's related to force, but it is not force. Voltage is that work necessary, and it's an expression of the potential energy available to do work in an electrical system. And that's that. All right, well, let's just bring this whole thing together. If the amount of work to move a coulomb of charge from one object to the other through the electric field that is caused by the charge difference between the two objects is 1 joule, then they say the potential difference between the two objects is 1 volt. So voltage is a measurement of the potential energy available to do work. So in our tank, the potential energy that is inherent in our tank of water, not the water itself, but the potential energy that's inherent in this tank of water is more like the voltage. And that potential energy that is inherent in that tank of water is experienced by observing its effect, which happens to be the pressure in the pipe. So there's no gauge that you can use to actually measure potential energy, at least none that I know of. But we can measure the pressure in the pipe, and knowing that pressure in the pipe, we can calculate the potential energy in the tank of water. And so voltage, no, it's not really that pressure in the pipe. The pressure in the pipe is an indication of the voltage. It is how we experience that voltage, but it is not equivalent to that. Voltage is an expression of potential energy available to do work. Now, in a moment, there is an extracurricular, extra credit section following this that asks the question, why is potential difference not the same as charge difference? So if you're interested in answering that question, just hang on, and it's coming up next. Thanks for listening. Toodaloots. All right, here's the extra credit homework. Why isn't potential difference the same as charge difference? Well, remember, you have two objects that have a difference in charge. One becomes positively charged relative to the other one. And an electric field is then between these two. Now, this is the equation for the strength of the electric field. It kind of looks like gobbledygook, but this is the charge. This is just a constant here. So, it could be the number 2 for all we know. but it is a constant relative to the particular situation we're in. This is the charge difference between these two. And then this is the distance between the two. Now you notice that here, this distance is squared. That means that if we take these two objects and separate them more, let's say that D goes from equal to 1 meter, and then we change D equal to 2 meters. Now, if the charge difference between the two stays the same, and this constant isn't changing, then the strength of the electric field goes from this times this divided by 1 squared, which is 1. So it goes from K Q diff to, now we're at 2 meters, which is twice as far. 2 squared is 4, and now we got a Q diff over 4. So by moving these apart twice as far, all of a sudden now our electric field intensity has dropped. It is now 1/4 of what it used to be. But we say, well, voltage is associated with work, and work equals force times distance. Well, the force that the electric field exerts on a charged particle in here, so we got our charged particle, the work that the electric field exerts, or the force that the electric field exerts on this charged particle, depends on the charge of that particle, but also the strength of the electric field. So that means that if we take these two and separate them twice as far, the electric field goes down to 1/4 of what it was, and the force necessary to move that particle also goes down to 1/4 of what it was. At the same time, so what we have in one case, we have, let's just say we got work is equal to force 1, that's originally. And then in our second case, work is equal to force 1 divided by 4. But now our distance has doubled. So what do we end up with? Well, this is F1D. This is F1D over 2 is what we end up with. So work is equal to F1 over 2 times D. So you take the same, everything's the same except you move these two apart, and all of a sudden the amount of work necessary to move that particle from one to the other has now gone down by 2. Therefore, the potential difference is half. Now, with that said, if you were to keep the distance between these two the same and simply increase the charge difference, yes, the voltage would go up. For every time you double the charge difference, the voltage would double. But if you're changing the distance between the two objects and not changing the charge difference, then the voltage actually drops by a factor of 2 if you double. So that's why they're not the same. Potential difference is not the same as charge difference. So there's the extra credit portion of this module.